guys, today we're going to run through a buffer overflow in Windows XP 32-bit. I'm going to show you how I find the buffer overflow through a process called fuzzing, and then how I exploit that to run my shellcode and get root access on the machine. Now, I'm a big fan of funny little metaphors, so I'm going to explain what a buffer overflow is using a diagram I made here real quickly. Now essentially what a buffer overflow is exploiting memory. It's taking advantage of somewhere that the programmer has stuffed up, hasn't allocated the memory properly, and we're going to exploit that. Now if you imagine here as a normal program, the way it would work is cars would come through, or a set of instructions in the program is completed. Once it's done, it moves on to the next step. Now, Mr. Policeman here, who's looking all angry, is the one that controls which step of the program is done and where we go next. So for example, say this part of the program is being run, Mr. Policeman would let these two cars go through, and then once that part of the program or the traffic is completed, he would turn around and then, for example, let these two through. Now, Mr. Policeman doesn't know where the next set of traffic has to go. What he does is he gets his information from the process that is just completed. So if we break each process, so to speak, down into two different steps, or two different cars, sorry. You've got one car that does the actual processing, let's say adding the digits together, and then you've got the next car that points out where the next avenue needs to go. So as these two cars come through, we would say add the numbers together, and then this car is going to say, hey, okay, now let down these cars. Now where the programmer stuffs up is this example here. We have three cars. So this program gets executed. This car tells the policeman where the next avenue needs to be done, but there's a third car here. Now in normal operation, if everything goes fine, third car just goes unknown, unmatched, program will still complete, still run fine, whatever. What we want to do is find where this third car is. So that means what happens is car goes through, does its job, this car tells the policeman where the next avenue is, then our car that we've now fiddled with tells the policeman again where the next process that needs to be done, but we can point it wherever we want. We're in control at this stage once we've found this car. Now the way to find this car, or where a programmer has essentially stuffed up with memory allocation, is a process called fuzzing. Now fuzzing is essentially taking a program, and where it asks for some user input, just giving it a whole bunch of random characters, throwing it too many digits, numbers, some weird characters, giving it some hex, whatever you can think of, and seeing if it breaks. If it breaks, chances are that there's a buffer overflow there that we can exploit. So, boot up Windows XP, and I've also got in the background here Kali running as well. And we're going to be exploiting the FTP server. These resources are available in the download link. We're also going to be using the immunity debugger. So first step, load these both into Windows XP's machine. Alright, first step, we need to make sure our computers can talk to each other. If they can't, chances are you've got the firewall on in Windows XP. So 192.168.207.130. Good, they can talk. Now, let's do our fuzzing process. Now, the way this FTP server works is it's on port 21, and when you connect to it, you send the word user and then your username. Instead of sending our username, say administrator or something, we're going to just send the letter A. But we're not going to send it once. We're going to start with sending it 50 times and increment that. So we'll send it 100, 150, 200, 250 over and over, and just see if the program breaks. Now to save you watching me type the program out, I've already made the initial fuzzing program here, and I'll just run through it with you really quickly. So this shebang calls the Python module. What it means is we can use the Python commands. We're going to use a socket. That's what actually connects to the machine, system, and time. We've set a variable here called target of the IP of the Windows machine, and I've called a variable called buff, and here's the letter A 50 times. Next, we've got a loop. What it's going to do is going to open a socket. We're going to set the timeout to 2 seconds. Now what this does is, if this fails, it's going to break this try attempt and bring it down to the accept section, which is going to tell us where it failed to connect. So pretty much it's going to connect over and over. When we can't, it's going to send us this. Here we connect, target IP, port 21, FTP server. This receives the banner. Then we've got our buffer. We're going to add our 50 A's because this is looping. We're going to print to the screen just how many A's we're using so far. Then we're going to send these A's. So send user, instead of the username, we're going to send the word buffer. Don't forget this /r/n, that means new line. Pretty much the server will just sit there thinking there's more information to come if you don't add that. We're going to then close the connection, wait 1 second, and repeat the loop. Alright, so let's run this and see what happens. Oh, actually, first let's start the FTP server. Cool. You might have to add file permissions to it, and then alright, so now we know that the program has broken. So we can see here, it stopped working, and it failed when 250 A's were sent. Now what that means is we know that somewhere between 200 and 250 bytes of data, the program just can't handle it anymore. It hasn't been designed properly. So what we're going to do is exploit that. Now for proof of concept, we're going to open up our immunity debugger here. So restart the FTP server, open up immunity, and what this is it is the way to view the assembly code of the program in real time. So we're going to file attach immunity to the FTP server, and here you go, you can see all the assembly commands that would be run as the program's running. Down here, program's paused, and these are the assembly commands: memory allocation, memory stack, and these are the registers. The registers are different parts, but the important one here is the EIP. Now this is a Mr. Policeman. This holds the next memory address of the program that's going to be executed next. What we want to do is take control of this EIP register. So we're going to come up here to press play, see our FTP server is running, and now we're going to send through those A's again and just watch what happens. Alright, so the program has failed again, and instead of crashing and burning, Immunity Debugger has actually paused the program at the crash. Now what we can see here is this EIP register is now 41414141. Now if you remember back to before, A in hexadecimal is 41. So what we've got here is the letter A 4 times as the EIP register. So that means somewhere in all those A's that we've sent, 4 of them have suddenly become the memory address that EIP thinks it's going to go next. Now of course this isn't a real address, so then the program crashes, burns and dies and all that kind of stuff. Down here we can see the EIP address and what it's got, and these are all the A's on the memory stack that we sent through it. Now instead of counting all those A's and working out exactly where these 4 are, Metasploit comes with a great little program called pattern create, so that we can work out exactly what 4 bytes are being used. Exactly the 4 bytes that are at that EIP, so then we can change them and tell the policeman, so to speak, where we want it to go next. So what we're going to do is create a unique string that generates characters so that we can work out which ones specifically are in there. For this, Metasploit has a cool little program called pattern create, and we know it was less than 250, so we'll ask for 300 digits. Cool. Now we've got a unique string. Go ahead and copy this. We'll go back into our fuzz, and now instead of sending a buffer, we're going to send this unique string. And we'll take off the A's. Save the program, go back to Windows, we'll restart the program with these double arrows up here. Program load, says pause down here, so we'll run the program. Now we'll run the fuzz again. Cool. Alright, now the IP, that's the hexadecimal, so A is 41, so whatever's 4 before A is that. Probably about 7. And then, so we've got the 4 memory addresses here, 37, 68, 41, 36. I'm going to copy that. And then the same way we generated this, Metasploit has a great little tool to tell us how many bytes in what we just recorded is. So user slash tools pattern, and this one's called pattern offset. And now we'll give it the hexadecimal representation of the digits we just got. Throw it in enter. And it's going to tell us that at exactly 230 bytes in, we have this memory allocation. So that's the 230 first byte, second byte, third byte, 4 byte. Cool. Alright, now let's prove this. So I've wrote up another, again, to save the programming time. Now what this is going to do is it's going to send through exactly, so we've got the A set to 230, so this is the offset, and we've got the letter B 4 times. Then we've got the letter C, a total of 500 minus whatever we've already sent. So this entire buffer is going to send through 500 digits. 230 of them are going to be A's, 4 of them will be B's, and the rest of them will be C's. Now if our offset is correct, if it's exactly 230, these 4 bytes of memory that are set to the B will take over the EIP. If it's the letter C or the letter A, then we know it's wrong. And back here, we know A is 41, B is 42, C is 43. So what we're looking for is 4 42s to be our EIP register. So we'll restart the program. And send through. Nope, buffer successful, cannot reconnect, we'll go back to the program. And look at that. B is 42, 1, 2, 3, 4. Perfect. You can also see here what is on the stack. So here are all our A's, here are the 4 B's we sent through that have become the IP, and here is where the ESP, or the information holding the data still to be loaded into memory, is. Now see how there's a gap here? So BBB, we've got 2 rows of C's before this row is called. That's important to note when we execute the shellcode later, and we'll come back to that. So now what we want to do is essentially take control of this memory address. What we want to do is point the EIP to where this ESP is, and then instead of the letter C, we're going to put in our shellcode. way we're going to do that is some people at this stage will just go, oh, okay, that's the memory address of the ESP at this stage. They'll just, copy the memory address, hard code it into the program, and go from there. That'll work in a virtual machine, it will work in this current environment, but in the real world, every time the program's run, it's put in a different spot of memory. So what we have to do is work out how we can get around this variable changing memory address. The way we can do that is there's a command in assembly that is jump to ESP. So what we want to do is find that jump command to the ESP, so that the way it's going to go is the EIP is going to run. We're going to get the exploit in the EIP, point the EIP to a jump to ESP command that already exists in the program, then that jump is going to run, come back to the ESP and run our shellcode. The way we do that is by searching through the program's assembly for it's called jump ESP command down here. Now, the easiest way to search through Immunity is using a little program called Mona. Now, Mona is a Python script, also in the resources. What you have to put it in there, all you got to do is download it, copy it to your clipboard, go to the program files of Immunity, and here where it says Py commands or Python commands, just paste it in here. So as you can see here, I've got the Mona, and then it's installed. You might have to restart Immunity Bugger, and then you'll be good to go. Now what we want Mona to do is to search for the jump command, jumping to the register ESP. And don't put it in capitals. Searching, searching, searching. Cool. Alright, that's run. Now technically what that's meant to do, and it might on your computer, is bring Mona to the front screen. For some reason it didn't, so what I'm going to do is I'm just going to run Mona, this is the Mona, and I'll scroll up. Now here we can see is the results for the jump ESP search. See, results, jump ESP. Now these are all the references or DLLs that the FTP server calls upon that include the jump ESP command and their memory addresses. You can theoretically pick any jump ESP from here. I tend to favor the shell32 and user32 DLLs, as there's normally no accessing permissions there, but theoretically you can use any of them. So using a user DSL, let's pick this one. This is the memory address that we're going to point the EIP to, that'll then jump back to the ESP. So it's going to go EIP to this, it'll run the jump ESP, go back to that. So let's copy this memory address and go back to our buffer overflow. Now, for those of you that were there for the live environment, the reason the exploit didn't work was because I had the loop running. I put the shellcode in the loop, which you're not meant to do. So what you need to do is delete these lines and take out the loop. I've already done that to save time here. So all I've done is taken out the while and the try, and I deleted the message that said sending the buffer overflow, and now I just, once it's all sent and closed, buffer sent. Alright, now the memory address, we're just going to put that in here, is that. Now, you can Google it later if you want to know the specifics of why this is, but the memory that we're viewing here is back to front. If we want to actually call on this memory address, we've got to go what's called little endian. So there's two types of memory addresses. There's long endian and there's little endian. To convert this to a format that we can use, we have to take each byte and read it backwards. Now because it's in hexadecimal, we need the /x. So it's going to be /x57, like that. The reason we're taking each 2 digits is that's 1 byte of hexadecimal. So now we have the memory address. What we're going to do here is send through the buffer, which is the 230As. Then we're going to send through our memory address. And let's type that correctly. And then what we'd be doing is sending the shellcode. /r/n. Now, coming back to where I showed you where those 2 rows of C's were, that bit of memory is going to get skipped. Now, we don't want our shellcode to begin directly at those C's. What we want it to do is start after where it was executed. So we're going to just throw in just a bunch of nothingness 15 times, just to ensure that our shellcode is fully loaded into the memory, and those, like the first 2 rows of the C's weren't, make sure it doesn't cut off our shellcode. Next thing we need to do is generate a shellcode. To do that, we're going to use Metasploit. I'm not going to run through the way Metasploit works completely, so you can just copy and paste this, but we're going to use payload, we're going to use Windows a shell bind TCP, and we're going to open up a port 2482. So MS payload, this is the payload we're going to run. This is the port we want to be opened on the target machine. And this little R is the format that it comes out. You can have R for RAW, you can have W for Windows. I'll just show you what the RAW looks like over here. Now, the RAW isn't going to be in a format we can understand, use, or paste into our program whatsoever. As you can see here, it's just a bunch of hoobity goobity. So what we need to do is encode this into a hexadecimal format that we can use. So we're going to pipe this into MSF encode -E for the type of encoder, 32-bit, because we're using a 32-bit machine, and the type of encoder we're going to use is this one. The way encoders are picked is through the type of or number of bad characters that you specify to the encoder. Now, bad characters are characters that when it's encoded the program won't use. I'm not going to go through how you work out what the bad characters are, as it's quite lengthy and tedious. So you're just going to have to trust me on this one. What I've done is I've already worked out what they are and put it in a file called badchars here. So I'm just going to copy this /B for bad characters and paste it in there. Now we hit enter and it'll generate our payload. Cool. Alright, payload is 366 bytes, and we'll just go ahead here and copy it all. Going back into the program, shellcode. Remember this bracket here, otherwise you're going to get real confused why it doesn't execute later. And then close the bracket here. This means that even though it's over multiple lines, it's all one variable, so to speak. Alrighty, so now we have the 238s that are going to be sent, us taking control of the EIP register, jumping to that user32 command we found for jump ESP, jump into the ESP, and then it'll run our shellcode, which will open up a port on the machine on port 2482 that we can then take control of. So save this, go back to the Windows machine, close Immunity, make sure the FTP server isn't running, and start it up again. Now that's running, jump back and run the shellcode. Now that the buffer's been sent, we'll use NC, stands for netcat, to remote in to the machine, and I forget the IP address. 192.168.207.130, and it was port 2482. So that was NC, IP address, port number. And there we go. Now we have our administrator root shell on the target machine. Just proof of concept, we can make a file. So we're in the desktop section. We can echo hello world to our, this is just going to write hello world to a text file called hacksaw. Been executed. Go back to the Windows machine, and look, there it is. So that's how you go through a buffer overflow. If you've got any questions, feel free to email me and I'll run it through for you. Hope you've enjoyed it. Have a good one.